Alright, continuing with this series of videos. A little bit late. Can't sleep, so we'll do physics. Although I'm tired. But anyway, we'll pretend I'm not. So I think we're up to lecture 20. So, on to the show. Oh, I probably should check the volume. Yeah, that's a good idea.
Today?
It'll probably be okay. I'll try to fix it if I see if it's still insufficient. It seemed insufficient in the last video, but we'll see how it goes.
I will quantify the ability of a circuit to fight the magnetic flux that is produced by the circuits themselves. If you have
Alright, so again, it's this idea of fighting, and it's not really fighting. It's you're just changing something. And by changing it, it produces a field of its own. And the two fields aren't, it's like putting two magnets the wrong way. They're not compatible. But there's no direct, the word fight just implies, I think, something that shouldn't be stated, because it's almost doing, it's just doing the mirror thing, and it's it's reflecting an image the other guy doesn't like seeing himself.
a circuit and you run a current through the circuit, then you create a magnetic field. And if the currents are changing, then the magnetic fields are changing. And so there will be an induced EMF in that circuit.
So again, I would just make it clear. The real difference between what we would theorize is happening, I'm saying the current is a byproduct of the creation of the pressure itself, and now the pressure has to be moved, and so it's moved, and that creates a current. But the current isn't some continuous thing or some eddy current or some other kind of current. The thing that makes the magnetism is the compression itself, or the decompression. The current is secondary. The current is how the decompression or the compression is removed, not what created it.
That fights the change. And we express that in terms of a self-inductance, L, self-inductance.
Alright, so self-inductance really just means inductance, okay? So it doesn't self-induce. It just, you run a current through a coil of wire, it induces a magnetic field. If you expose the coil to a field, the field will induce a current, vice versa. But what's really being induced is pressure or an absence of pressure.
And the word self speaks for itself. It's doing it to itself. Magnetic flux that is produced by the circuit is always proportional to the current. If you double the current, the magnetic flux doubles. And so it is the...
So again, you could look at this as a, if you had a coil of wire and the current's going through the coil of wire, and as it goes through, it's magnetizing the wire. That magnetism is going faster than the current, and it's pre-pressurizing the coil ahead of it, which is essentially creating a resistance to the current moving because there's pressure ahead. So it's, it's just a retardation created by the fact that the current moving isn't going to move as fast as the speed of light, and therefore, especially if it's going in a spiral like this in a wire, and so the magnetism is going to be ahead of the current, and it's going to pre-charge the wire, the conductor, before the current gets there, and by pre-charging it, it's going to create resistance to the migration of the voltage.
Proportionality constant that we call L. That is the self-inductance. And so therefore the induced EMF equals minus d phi dt. That is Faraday's law.
d phi dt.
And so that becomes minus L.
So again, they say this, and it just never, that doesn't look like a d phi bt. I don't know what a dt, d phi, so this phi with the b under it, it doesn't seem like those both should have the same name, but whatever. So that's the flux of the B field. So you have, well, no point. There's really no point, because yes, most of this is, they end up being constants.
L, the IDT. L is only a matter of geometry. L is not a function of the current itself. I will calculate for you a very simple case of the self-inductance of a solenoid. let this be a solenoid, and this is a closed circuit, and we run a current I through the solenoid, and the radius of these windings is little r. Let's say there are n windings, and the length of the solenoid is little l.
So again, you have to have some more assumptions built into this mathematics, which is the assumptions are usually that this solenoid doesn't have a bunch of air gaps in it.
Perhaps you remember that we earlier derived, using Ampere's law, that the magnetic field inside the solenoid is mu0 times I times capital N divided by L. This is the number of windings per meter. If we attach an open surface to this closed loop, very difficult to imagine what that open surface looks like. We discussed it many times. Inside this solenoid you have sort of a staircase-like of surface. That magnetic field penetrates that surface n times, because you have n loops. And so the magnetic flux, phi of B, is simply the area pi little r squared, which is the surface area of one loop, because I assume that the magnetic field is constant inside the solenoid.
So again, that's an assumption, and it's an assumption based on that somehow your L and N numbers are rational, in the sense that you don't have 3 N's for a meter of wire. So there are assumptions built in.
I assume that it is 0 outside, which is a very good approximation. So we get pi little r squared, surface area of one loop, but we have n loops, and then we have to multiply by that constant magnetic field. So we get an n squared, because we have an n here, mu0I divided by L. And this we call L times I. That's our definition for self-inductance. And so the self-inductance L...
Call it L times I. So I don't know exactly how the mu0 over L got turned into L times I, but okay, fine.
It's purely geometry. It's pi little r squared, capital N squared, divided by L times mu0.
So mu0 is half the speed of light. The pi r squared is also a number that's pretty close, so you go, well, no, the pi, no, that one won't work. The 2 pi, whatever, squared was the one that was the other half of the, anyway, the mu0 times the epsilon 0 ends up being the speed of light over 1.
Let me check this. Pi little r squared, the capital N squared, mu0. That's correct, divided by little l. And so we can calculate, for instance, what this self-inductance is for a solenoid that we have used in class several times. We have
right, and it'll be in a form of whatever, newtons per square meter or some other form that this formula is sort of made to produce. So, you know, I think there's a simpler way of diagramming the fact that the self-inductance will deter by a certain percentage of, you know, how fast the inductor charges, and then how fast it can discharge, because it's basically turning into a battery.
One whereby we had 2,800 windings. R, I think, was something like 5 centimeters. You have to work SI, of course, be careful. And we had a length was 0.6 meters. We had it several times out here. And if you substitute those numbers in there, you will find that the self-inductance of that solenoid is 0.1 in SI units, and we call the SI unit Henry, capital H. It would be the same as volt seconds for ampere, but no one would ever use that. We call that Henry.
Yeah, volts seconds, I don't know exactly what that would mean, but except voltage going across something that's almost like a current number if you're going volts per second. Over area, did he say? Yeah, I don't know. I don't remember what the A was.
Every circuit has a finite value for the self-inductance, however small that may be. Sometimes it's so small that we ignore it. But if you take a simple loop, a simple wire that goes around, whether it is a rectangle or whether it is a circle, it doesn't make any difference, it always produces a magnetic field. It always produces a magnetic flux through the surface. And so it always has a finite self-inductance. Maybe
you could argue that every piece of the circuitry, okay, when it's got current running through it, and that's the rule, because that's what polarizes it, that's what charges it, that's what changes the atoms from 5s to 3s, or however you want to look at it. It makes an atom a black atom versus being a red atom, a electron strong versus a proton strong atom, and that creates a field depending on how aggressive that changes. Voltage wise, how much pressure, how much you've compressed or how much you've expanded the atom.
Only 9 nano henries, maybe only micro henries, but it's never 0. And so now what I want to do is to show you the remarkable consequences of the presence of a self-inductor in a circuit. And I start very simple. I have here a battery which has EMF V. I have here a switch, and here I have a self-inductor. We always draw a self-inductor in a circuit with these coils. And we also have in series a resistor, which we always indicate with these teeth. And I close this switch when there is no current running. In other words, at time t equals 0, when I close the switch, there is no current. When I close this switch, the current wants to increase, but the self-inductance says, take it easy, Lenz's law, I don't like the change.
Okay, so I would argue that change is moving through the wire towards the coil. As the coil starts to charge, it's obviously going to affect the wires ahead of it. The same field it's producing inside, it's producing perpendicularly, or next to the wire right next to it. And so it's pre-charging the wires ahead of it, which means it's lowering their voltage potential, in the sense that whatever voltage is moving, high pressure to low pressure, or whether you want to think of it as low pressure to high pressure, it doesn't really matter. The point is it's lower pressuring or high pressuring the thing in front of it, which means it's making it more difficult for the voltage change to move, because there's not enough difference in the voltage. The pressure is being reduced. It's a form of suppressing the speed at which the event takes place, in a sense, because of the fact that the voltage differential is being retarded.
Of such a current. So the self-inductance is fighting the current that wants to go through it. There comes a time that the self-inductance loses the fight if you wait long enough, and then of course the current has reached a maximum value, which you can find with Ohm's law. Because the self-inductance itself has no resistance. Think of the self-inductance as made of superconducting material. There's no resistance. And so
So whatever that even means, I don't know how this no resistance thing happens. But anyway, so once the coil has regularized the pressure of the inductor, then the current can move at some rate, but it's still going to be a rate lower than a straight piece of wire would be.
Knowing much about physics, you can make a plot about the current that is going to flow as a function of time. You start out with 0, and then ultimately, if you wait long enough, you reach a maximum current, which is given by Ohm's law, which is simply V divided by R. And you slowly approach that value. And how slowly depends on the value of the self-inductance. If the self-inductance is very high, it might climb up like this, so there is a high value for L. If the self-inductance is very low, that is a low value for L. If the self-inductance was 0, it would come up instantaneously. But I just convinced you that there is no such thing as 0 self-inductance. There's always something finite, no matter how small. And so this is qualitatively what you would expect if you use your stomach and if you don't use your brains yet. There's nothing wrong with using your stomach occasionally. But now I want to do this in a more civilized way, and I want to use my brains. And when I use my brains, I have to set up an equation for this circuit. And if you read your book, you will find that Mr. John Coley tells you to use Kirchhoff's loop rule. But Mr. John Coley doesn't understand Faraday's law, and he's not the only one. Almost every college book that you read on physics do this wrong. They advise you to use Kirchhoff's loop rule, which says that the closed loop integral around the circuit is 0. That, of course, is utter nonsense. How can it be 0? because there is a change in magnetic flux. And so it can only be minus d phi dt.
So this gets to this other subject of the fact that you could use the self-inductor as a cause of current, or a cause of induction. You can use it to induce in other objects because it creates a magnetic field. But as pointed out, the magnetic field coming off the outside of the inductor is very weak. So it's going to have very little effect as a practical matter on the rest of these wires. So the only wires it's going to have a real effect on are the ones that are parallel in the loop. So the effect is going to be contained to the wires inside the loop.
I advise you to go to the 802 website and download the lecture supplement that you will find, in which I address this issue and hit it very hard. So the closed loop integral of E dot dl, if you go around the circuit, is not zero, is minus d phi dt, Faraday's law, so it's minus L the I dt. So we have to go around the circuit and we have to apply Faraday's law and not Kirchhoff's loop rule, which doesn't apply here. This is the plus side of the battery, and this is the minus side, so the electric field in the battery is in this direction. The electric field in the self-inductance is zero, because the self-inductance has no resistance, it's superconducting material. And so the electric field in the resistor, if the current is in this direction, which it will be, then the electric field in the resistor will be in this direction. So now I am equipped to write down the closed loop integral.
So again, they just keep talking in terms of this electric field, and all there really is voltage. And the voltage, the pressure, the 5 atoms have to exchange with a 3 and turn the 3 into a 5, and that turns the 5 into a 3, and it moves that 5 progressively down the wire. So what's happening is the 5s keep going that way, or that way. The point is you're just moving the pressure.
Integral of E dot dl. I start here, and I always go in the direction of the current, and I advise you to do the same.
I mean, every time there's an exchange from a 3 to a 5, you can understand that's a north to a south, north to a south. So it's just constantly changing the magnetic poles down the wire. So it's moving little magnets down the wire, in a sense.
I don't care that you guess the wrong direction for the current, that's fine. Later, minus signs will correct that. They will tell you that you really guessed the wrong direction. But always go around the loop in the direction of the current, because then the EMF is always minus L di dt. If you go in the direction opposed to the current, then it is plus L di dt, and that could become confusing. So
I think the point is here, if you do Faraday, you have to do the integral, and if you do the loop rule thing, you don't have to bother with integrals. So if you're going to get the same answer either way, it's probably a lot easier just to do the cheat.
Always go in the direction of the current. And so I first go through the self-inductance. There is no electric field in the self-inductance, so the integral E dot dl, going from here to here, is 0. This is where the books are wrong. It is 0. Now I go through the resistor, and so now I get plus IR. E and dl are in the same direction. Ohm's law tells me it's IR. In the battery, I go against the electric field, and so I get minus V. That now equals minus L di dt. And this is the only sane and the only correct way to apply Faraday's law.
So he's just saying you're connecting two different things. What's in half the circuit equals what's in the other half, which essentially is one's going to be a negative number and one's going to be a positive number, and you're still going to end up with a 0 loop rule, I think.
In this circuit. You could write it a little differently, which may give you some insight. For instance, you could write that I can bring V and the L and L to one side, so I can write down that V minus L di dt equals IR. It's the same equation when you look. And the nice thing about writing it this way is that since the IDT is positive here, it's growing in time, the induced EMF, which is this value, notice it's always opposing the voltage of my battery. And that's what Lenz's law is all about. It's not until the IDT has become 0 that V equals IR. And that happens, of course, if you wait long enough. And so we have to solve that differential equation. And what is often done, that you bring all the terms to the left side and that you get a 0 on the right side. And so what you often see is that L the IDT plus IR minus V equals 0. And because we have a 0 here, some physicists think that this is an application of Kirchhoff's rule, which is nonsense. You can always make...
Well, it sort of is, except you just put in this DDT term. That's basically the time it takes. The only timed element in the circuit is the inductor. It's the only thing that's wasting time. The other circuits are what they are. The resistor is just doing its resistance thing.
It's 0 here by bringing all the terms to this side. The closed loop integral of E dot dl is not 0. The closed loop integral of E dot dl is minus L the IDT. But when I shift minus L the IDT to this side, I get 0 here. And of course, the people who write these books know that this is the right answer, and so they manipulate it so they get this equation, and they call that Kirchhoff's rule. Sad.
Well, it's the same thing. You're just using a different term for the DI/dt thing, which they had to account for anyway in the loop rule. So I don't see the difference.
And also embarrassing. So this is the equation that you have to solve. Some of you may have solved this equation in 801 already. Surely you didn't have an I here, you may have had an X here for the position. But you probably solved it where you had friction. Maybe you didn't. I will give you the solution to that differential equation. It's a very easy solution. The current as a function of time is a maximum value times 1 minus E to the minus R divided by L times T. And I max...
Oh yeah, that's really obvious. Jesus. Minus R over L times T. Okay.
The maximum current is V divided by R. And let's look at this in a little bit more detail. First, notice that when T equals 0, that indeed you find I equals 0. Substitute in here T equals 0, you get 1 minus 1. So you find indeed that I equals 0. Substitute in there T goes to infinity, then you find that I indeed becomes V divided by R, which is exactly what you expect. If T becomes infinity, then clearly the self-inductance has lost all its...
Right, so you're just figuring out how much time it takes to get over the fact that the wire is in flux until you get the current through it, and then it becomes a better conductor. But it doesn't conduct very well at first because it's producing a magnetic effect ahead of the voltage, which is making it difficult for the voltage to pass through the wire.
Power, so to speak, and the current is simply V divided by R, the maximum current that you can have. And so that's a must, that's a requirement. If you wait L over R seconds...
See, the catch is the time is really deceptive, because you could argue that the time it's taking for that current to get through is in the process of making that magnetism. So that process takes time to pressurize and depressurize, so you're creating a magnetic field inside of the coil, and that field lingers. So like a capacitor, when you turn the circuit off, that coil still have energy in it, and so you're essentially going to give you back what it took away. So the delay energy is in the coil itself, and it will be given back. Like in a capacitor, you'll get it back if you once you cut off the circuit, you'll still have voltage caught in that coil.
And believe it or not, if you have some time, convince yourself that L over R indeed as a unit is seconds. Then the current I is about 63% of I max. Because if T is L over R, then you get 1 minus 1 divided by E, and that is about 0.63. And if you wait double this time, then you have about 86% of the maximum current.
So, so if your current's going down, it means your voltage has to be going up to create the same amount of energy, presumably. And so that might be the difference.
In other words, right here, if I wait L over R seconds, this value here is about 0.63 times the maximum value possible. And it's climbing up and asymptotically approaches then ultimately the maximum current, which is V divided by R. Make sure you download that lecture supplement that you...
So the voltage would drop and the current would go up to have the same watts coming out of the system, presumably.
You'll find on the web. Now, what I'm going to do is all of a sudden I'm going to make this voltage 0. The way I could do that is by simply shorting it out. Of course, on the blackboard, I can...
Well, you disconnect it. Shorting it out would be a mistake, right? Shorting out a battery.
simply remove it. So it's not there, the current is still running, and all of a sudden, at a new time t0, I define the time t0 again, the voltage is 0. And now comes the question, what is now going to happen? Well, the self-inductance doesn't like the fact that the current is going down, so it's going to fight that change.
So again, it's this fighting change, and there's no fighting change. There's energy stored in the coil. So the coil is producing a magnetic field. The magnetic field is in progress. It already shot its load, so to speak. And yes, it's moving the speed of light and all that, but it's still, it put energy into the field. And especially as a core or something in it, then it's magnetized the core. And that, when you turn the current off, that's coming back. Because of the idea that, as told you before, these things are reflecting inside of the coil, and they're going to keep on reflecting until they die out. You know, there's some misses, so they hit and miss and miss, 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 but there's mostly reflections, and the reflections aren't perfect because of temperature. So if you could super cool it, then it would be kind of interesting to see what would happen. But the reflections are going to die out, and your current will drop off. But you're getting your energy that it appeared not to have at the initiation of the circuit. You're going to get that back.
And so you expect that the current is not going to die off right away, but you expect that the current is going to go down sort of like so. And you want, when you wait long enough, you want that at t goes to infinity, so at t equals 0, the current is still maximum, so it's still V over R. But when you go to infinity, if you wait long enough, then of course the current has to become 0. And as the current dies out, heat is being produced in that resistor at a rate of I square R joules per second. And then there comes a time that the current becomes almost 0, and then the whole show is over.
But the point is the energy stored for this event to take place after the battery's been disconnected. Again, the battery's disconnected. There's still current flowing through the wire, and that current is coming from the energy stored in those reflections that are happening inside the coil.
And so we can also calculate the exact time behavior by going back to our differential equation and make V0. Where is that differential equation? Is it hiding? Oh, there it is. So I solve this differential equation, but this is now 0. And the solution to that differential equation...
Well, obviously the voltage in the circuit isn't 0, just in the battery. So, yes, 1V is 0, but not the V of the circuit.
Is that I, as a function of time, is I max times e to the minus R over L times t. And that exactly has all the quantities that you wanted to have. Because notice that at t equals 0, when you put in t equals 0, the current is indeed maximum. And that's what you require. That's the moment that you make that capital V0. The current will still...
Right, so this equation is just saying when you cut the current off, let's do a new equation, and these will be the current you're going to get back, and it's kind of the inverse of what happened when the coil was energizing, and now you're de-energizing it, and you're going to get back pretty much what you put in, essentially.
Running. But notice that when t goes to infinity, you wait long enough, that indeed the current goes to 0. And if you wait L over R seconds, then you are down to about 37% of your maximum current. So if you now go, so I redefine t equals 0 here. So if now I wait L over R seconds, then this value here is about 37% of that value. So you've lost 63%. And so you see, this is the consequence of the fact that the circuit is capable of...
So you could only get 63 by his example going up at that time, and you lost 63 going down. So it's exactly the same proportion. So essentially, but I would argue that's probably an ideal world, and not the actual fact. You don't get back all that you put in.
Fighting its own magnetic flux that it is creating. When the current was running happily here with the battery in place, the current was, let's say, all the time I max. At least very close to that value, V over R. And so all the time...
See, at least very close to that value. Like I said, I'm not even sure it is exactly I max is exactly as much you get with a straight wire. It's probably a little retarded.
There was heat produced in the resistor, I square R joules per second. Who was providing that energy? Well, of course, the battery. But now, when I take the battery out, there is still current running. And that means while the current is dying, there is still heat produced in that resistor. And that heat slowly comes out until the current ultimately becomes zero. Now where does
So again, it's not really coming out through the resistor. You could take the resistor out of the circuit and the inductor would still drain if you had the pole of the battery. You had something connected for it to drain too. It would drain.
that energy come from? Well, that energy must come from the magnetic field that is present in the solenoid. And this idea that we have energy...
So it sort of proves my point. Like I said, it really couldn't be... If all it was radiation that just kept going, at the speed of light, you can sort of understand if I have a coil of wire and the radiation just hits the other wire on the opposite side and then keeps going, and so there's no reflections, you'd understand that that would happen so quickly that whatever that was, that one reflection, that couldn't maintain any kind of constant current. So you need to be able to collect a whole bunch of these things bouncing back and forth inside of that coil. It has to be quite a collection of it for you to have any durability in terms of that current being maintained, draining that. So it sort of emphasizes, it sort of proves my point, I think, that the reason why you have that much energy in there is because it is reflecting, kind of like a laser beam or something other form where you reflect energy back and forth and you just keep reflecting it and reflecting it, so you're adding to its volume. The constant reflections mean you've trapped it as energy and it's still there.
that comes out in the form of heat, which really was there earlier in the form of a magnetic field, allows us to evaluate what we call the magnetic energy field density. Let me first calculate.
So let's just say there's this first beam that's created by the current. First beam goes out, and then the second little voltage thing, second beam goes out, third beam goes out. They just keep piling up and they keep reflecting. And so where you just had one, that would just disappear and that was it. And we had one impact, it's over, it's done. You're adding and adding and adding. So you have 100 or 200 or 1,000 or 1,000,000 of these little things now. And so now you have to drain all 1,000,000. That means that one that it hits, it creates voltage in the other wire. The voltage goes out through the resistor. So now it's being collected. So it's not reflecting by the coil anymore because the coil is draining it. So the reflections are stopping because the coils on each rebound are absorbing it and sending it off to the resistor. So it's not even that there's misses or there's drainage in any other way. The drainage is really going to be quite specific. But I would guess that you can't hold current inside an inductor very long. So if you charged one up and just left it charged and disconnected, that it's not going to hold that charge anywhere near indefinitely because it's going to leak out the two ends.
How much heat is produced as the current goes from a maximum value down to zero? I'll have to rate.
So now he's just going to come up with a way of measuring how much energy was stored inside that inductor. And clearly it's to have a constant number, you have to get it up to its maximum. So just like a capacitor, you have to charge it all the way before you can measure how much the capacitor can hold. So if the inductor is charged all the way, then you can measure, by measuring the resistor, how much energy is being dissipated by the resistor. You can measure a proportional relationship between how much energy obviously came out of the coil. It's just giving you a way of measuring the proportionality, having some measurement and saying the resistor is going to be equal in volume proportion to the proportion that was in the coil itself.
It's something. I will raise this part here. So at any moment in time, the current is producing heat in the resistor, and so if my voltage becomes 0 at time t equals 0, then this is the amount of heat. No square here. I square R dt integrated from 0 to infinity is the total heat that is produced as the current dies out. But I know what this current was. I just erased it. I still remember it.
I don't know why they do integrals to infinity. I don't even know how that's possible, but whatever. I guess you just give up averaging after a while. You just say after we average 4 times and we combine our 4 averages and then multiply it by 4, then we can say we're done or something.
So I can bring I max outside, and I can bring the resistance outside, and then I get the integral from 0 to infinity of e to the minus r over L times t dt.
Yeah, I can't make anything out of that. I don't know how you do this L to a power of something other fractions and crap, so I have no idea what that could be.
And this is a trivial integral. This integral is L divided by 2r. Oh, by the way, it is I squared, so I have a 2 here. It's very important. Don't forget the 2. And so that integral is L divided by 2r. And so if now...
Alright, so now he's converted the length n into 2r, so 2 times the resistance, divided into the length. So that's making the resistance a lot bigger, twice as big, and dividing that into the length of the wire, the coil, and that's the proportion of how much... I still don't know how that's going to give him how much heat was dissipated by the resistor, but whatever, we'll see.
I look at the product of I square maximum R L divided by 2R, I get 1/2 L times I maximum squared. So this comes out in the form of heat.
Alright, so it's a half, which is good, because if you're going to get a monster number by squaring the current. And then you're going to cut that in half. So it's just telling you how many, that's sort of telling you how many reflections are inside there. So the I being squared is essentially saying, yeah, this thing happens a lot. This back and forth thing. Over time, the longer the time, the more of this you got, because you got up to the maximum amount, so there's a certain amount of time. And you'll have a certain volume. For the size coil you have, you always have the same volume. And then you're just going to divide that by the...
and I max is then the maximum current that we had.
You're going to cut it in half, yeah.
When the current was flowing after a long time.
And you're going to be multiplying it times the decimal number, which is L. L is going to be 30 centimeters, 0.3 meters. So that's going to reduce the number again.
I can now, by manipulating numbers, I can now calculate how much energy there was in that field per cubic meter, because the magnetic field was exclusively inside that solenoid. And if I know that the energy that is ultimately coming out is 1/2...
So it wasn't exclusively in there, so that's again just wrong. There is a field on the outside, it's just incredibly weak compared to the reflected field on the inside. So without the reflections that are happening on the inside field would be weak too. But because of the reflections, it's essentially trapping energy.
L I squared, then I have here I, and so I can replace that I there by B divided by mu 0 times L divided by N, and here I have L. And so if I substitute in here the value for L that we have on the blackboard there, and we substitute for I the value that we have there, you can drop the maximum now. This simply tells you then that any moment in time that I have a current I running through a solenoid, that the energy that is available in the solenoid in the forms of magnetic energy is 1/2 Li squared.
Well, I mean, obviously it matters because that's going to be the timed issue. So if you reduce the amount of the I max, you're just basically, that's a substitute for time. So if you're somewhere less than I max and you're some lower number, then obviously you haven't even charged you haven't charged all the way, but you've charged it that much for that much time. So it's a way of putting the time in without putting the time in.
And so when you do that, you substitute capital L and capital I, you will find that 1/2 Li squared then becomes B squared.
I don't know why it has to become B squared. So I don't know why that happens. I mean, I don't know why you wouldn't just solve that. The L times the I squared seem like as simple as you possibly want the equation to be. Why would I need it any simpler than that? 1/2 L times R squared. I mean, that just makes it so simple.
Over 2 mu 0 times pi little r squared.
So you have L times the current squared. 1/2 L times the current squared. Why wouldn't you just keep that? That's really simple. Incredibly simple. Why would I do all this other extra stuff for? What do I need all that extra shit for? I got a simple thing to solve. The L I know, and I know that I can measure the current. So I'm done. Why am I doing all this pi r squared epsilon 0 crap again for? See, this is what I don't understand. You know, why these derivatives? They're trying to solve for some variable, and you just sometimes would argue, well, I already know the variable. Why would I do the derivative when I know the variable?
Times L. You check that at home. It's simply a substitution. But this.
So now we got B squared over 2 mu 0. So that's the permeability of space or something. It's a relatively small number. Into B squared, which is going to be B in what form? Henry's or what? And we got pi r squared L. I don't know exactly. I guess that has to do with the circular part. I mean, the fact is that the stuff is going to be happening in radians in 360 degrees. So you're storing energy in 360 degrees inside the coil. That would be the assumption.
Is the volume of the solenoid where the magnetic field exists.
Exactly. So that's the volume inside, and the length times the circumference. And times, so you got the volume times some fake constant divided into the magnetic field squared, which is a substitution for L and I. Well, I'm not going to bother trying to figure that out. I mean, this capital L and this L, I don't know what the difference between those two are.
We assume that the magnetic field is zero everywhere outside. And if you accept that, then you see that we now have a result for the magnetic field energy density. That is how much energy there is per cubic meter. That is, of course, this value.
Well, why would I care? I'm more concerned with how many watts I might get out of it. How many watts are stored in the inductor? That would probably be the most important number to know.
Because this is the total energy of the magnetic field, if we know the current, and this is the volume of the magnetic field. So the magnetic field energy density is then B squared divided by 2 mu 0, and this is in joules per cubic meter. So in principle...
Right, so joules per cubic meter converts into watts somehow or other, but I don't know exactly how to do that.
If you knew the magnetic field everywhere in space, then you can integrate over all space, and you can then calculate how much energy is present in the magnetic field. And earlier in this course, we did something similar for electric fields. We calculated the electric field energy density. Perhaps you remember what it was. It was 1/2 epsilon 0 kappa times E squared. It was also in joules per cubic meter. Now, in the case of an electric field, this represents the work that I have to do to arrange the charges in a certain configuration. In the case of a magnetic field, it represents the work that I have to do to get a current going inside a pure self-inductor. That means...
So again, he's still talking in terms of a current going when all you're really doing is charging the atoms.
The resistance of the self-inductor is 0. And it takes work because the solenoid will oppose the building up of the current. And so I have to...
Again, it's not opposing that, it's the voltage is dropping inside the inductor. And, no, the voltage is increasing because of the fact that it's the pressure is being pushed forward by the magnetic. These coils here are now charged. They're imposing a charge on the coils in front, and the voltage has to push through that, and so it has to increase. So that means it has to be retarded, that is compressed. So the voltage increases. So the voltage wants to go through. It can't because this is already compressed by the field, the magnetic field, the charge field, however to describe that. It's not an EMF. It's not an electromotive force. It's I don't want to use their rhetoric because they're not understanding what the actual cause is, which is atoms being charged. So the point is just that to break through that barrier, this voltage will increase. Because it has to, because it's backed up until it does. A 5 can't do anything with a 5. There's no interaction between a 5 and a 5. It needs a 5 and a 3. So if this is already a 5 and this is a 5, this one has to get pushed more to be a 6, and then it can make a exchange with a 6. A 6 and a 5 can make an exchange. But it can't make an exchange if they're at the same pressure. So it has to break through by increasing the voltage inside the coil. Not inside, not in the circuit, just inside the coil.
To work. So there's a parallel between the two. I can make you see, in a quite dramatic way, how strong self-inductances can fight their own current. And the way I'm going to do that is with a setup there, whereby I have a 12-volt car battery, and I have 2 light bulbs. I have here an enormous self-inductance, L, 30 Henry. We will learn later in the course how you make such a high self-inductance. And then here is a light bulb. The light bulb has a resistance of 6 ohm. This self-inductance, there is nothing we can do about it, happens to have 4 ohm resistance. We don't have superconducting wires here. So it also has a resistance of 4 ohms. Forgive me for that, but there's nothing I can do about it.
Well, I know, but you should have been honest that all the inductors have some resistance. So why ever talk about superconductors anyway? That always should have been part of the equation, frankly. I don't see why that was... I mean, I understand you want to make it one bit less complicated, but I mean, these shortcuts sort of can be deceptive.
I have here another resistance of 4 ohms, and a light bulb, which is the same one as that one, also 6 ohms. And then here is my car battery, plus a switch. And the car battery is 12 volts. And I'm going to throw the switch, turn it on. You will see that this light bulb comes on almost instantaneously. There is no self-inductance in this loop, well, maybe a few microhenry or even less. But in this loop here, there is this huge self-inductance. And so the self-inductance says, take it easy to the current, take it easy, just wait, and you will very slowly see that light bulb come on. And we can calculate how long it takes. Because we have here 10 ohms, 6 ohms, and 4 ohms, so L divided by R is 30 divided by 10, so that is 3 seconds. So what that means is that even after 6 seconds, which is twice this time, even then, the current through this light bulb is only 86% of its maximum. But that means, since the light, of course, is proportional to I square R in the light bulb, that the light is only 75% of maximum. And even if you wait 9 seconds, then the light that comes out here is still only 90% of its maximum, whereas this one comes on immediately. The reason why we put the 4 ohm here, we want this part.
So the part that would be interesting to measure is to measure the actual current that goes to the coil rather than the current that comes out of the light bulb. Because this current going into the coil is actually, at the time he's saying the current is only 1/6, and no, it's the current is going into the coil and actually creating a real wattage through that coil. So it's consuming energy from the battery at the real rate, not 30%. It's just storing energy. It's creating a battery itself, and so it's takes time to get through the coil because it has to excrete this field.
To be, from an ohmic resistance point of view, to be identical as this part. So that's why I artificially added here the 4 ohm, because the 4 ohm is always there in the self-inductance. There's nothing we can do about it.
Well, I can't say for sure that that's even necessary, frankly. I'm just trying, I mean, obviously, the reflecting part is what makes that coil so much more powerful than a straight wire. So you have to just say that's almost free energy because it's all reflections. And the real resistance is just in the fact that the pressure can't move through a pre-pressurized wire. So if it's moving towards a negative, right? It's going from positive to negative. Well, if it's pressurizing the wire in front of it, it's not a negative anymore. So it's not moving from a positive to a negative. It's moving to a positive to a positive. And that's where the problem comes in. That's why it retards the progress of the current.
And so you're going to see a remarkable example. This is one light bulb. That is the one that is here. And this is the light bulb that is there. And the self-inductance is in this incredible monster here. I'll make the lights, change the light setting a little bit so that we can see the lights of the bulbs. The bulbs are only 8-watt bulbs. They're not very, very strong, not very bright bulbs. But the effect will be very clear. So if you're ready for this, so this is the one that I think comes on immediately, and this is the one that takes its time. 3, 2, 1, 0. 1, 2, 3, 4, 5, 6. You see how slowly it's still not very bright. Still getting brighter. Still not as bright as this one. It's getting there. We can actually do some timing by counting.
So you saw that one died out much slower. So let's just play that one more time real quick. So watch how fast the bulbs die
This is the one
when he
that
turns
takes
it
its
off.
time. 3, 2, 1, 0. 1, 2, 3, 4, 5, 6. You see how slowly it's still not very bright. Still getting brighter. Still not as bright as this one. It's getting there. You can actually do some timing by counting.
There. Well, yeah, they both took a little time to cool off.
By the way, the values of the resistance that I gave you are when the...
So the problem is he's not really disconnecting the coil. So the coil, he's not disconnecting it from the circuit. So the energy's just running out. He's turning one lead from the battery off. And so the energy can still leak because the two are connected. I'm trying to think of how the two are connected. Once they're connected through that 4 ohm resistor. So it's going backwards through both bulbs.
Light bulbs are hot. 3, 2, 1, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm still seeing it getting brighter. So what you're seeing here is a remarkable example that the self-inductance is fighting the change in current.
So it'd be more interesting to cut the self-inductor off the light bulb. No, that wouldn't help. Well, one away the other. Point is that there's energy stored in. Well, we already demonstrated how there's this current that keeps flowing, so I don't have to make this argument that that's what's happening.
That's why the name self-inductance is so nice.
Alright, so that's probably enough for getting on the hour-ish mark. I could probably finish, but I think I won't. And so we'll wait for the next segment, which I think might be on the eddy currents inside of paramagnetic material, some more on that stuff, which is an interesting subject. Lots of details, and it does seem like it's a very underexplored in terms of all the different ways you could do the experiment and see what effects it has. And I guess it's the kind of thing I'm going to have to do someday. Anyway, until the next time, and such.